Good afternoon, everybody. So in the last class, we have seen Faraday's law of induction. We have seen that if you have a loop and if you're going to change the magnetic flux through that loop, then that will result in an induced EMF and an induced current in this loop. And all through, I kept talking about a loop which is not having an EMF, which is not having an EMF source. It is not having a battery. This is what I kept insisting from the beginning. But then today we can make a small distinction and say that what if there is an EMF source, then what happens? That's what we'll be discussing today. And the next thing we'll discuss is what is the direction of the induced current? Is it this way or this way? What decides the direction of the induced current and EMF? So that's what we're going to see. And to answer that question, we will have to go back to the observation. Okay. In our experiment number 1 and 2 of Faraday, we have seen that whether it was North Pole or South Pole that was facing the loop, it mattered. Then again, whether you were moving it into or bringing it out mattered. The speed at which you were increasing and decreasing also mattered. Okay, so somewhere directionality is involved. Okay, so we can sum up all this and say that the direction of the induced EMF and induced current depended on the direction of the magnetic field and whether the magnetic field was increasing as a function of time or decreasing as a function of time. Of course, we stopped using the word magnetic field. We were talking in terms of magnetic flux, where magnetic flux was integral B dot D A. Okay, so instead of talking about change in magnetic field, we can talk about change in magnetic flux. That will be more general, and why it is so, that we'll discuss a little later. So let us say that the flux is increasing as a function of time. If it is increasing as a function of time, then d phi d by dt will be positive. That is, always change means final minus initial. So if the flux is increasing, that means final flux is more than the initial flux. So final minus initial is a positive quantity. Positive divided by time is a positive quantity. Similarly, if the flux is decreasing, then you say that d phi by dt is negative. If flux is decreasing. This is if flux is increasing. Okay, like for example, look at this picture here. When you are moving the bar magnet into the loop, so this is your loop. When you are moving the bar magnet into the loop, when you're moving it towards, you can see that more number of, just think of it, when the North Pole reaches here, all these flux lines would be cutting through this loop. Or in other words, the flux is increasing as a function of time. Now look at the second picture. Okay, so let us see the effect of this flux increase. Okay, when you move it, you're going to see a current. Okay, and let us assume that this current is as given here, that the current in the loop is in this direction. What is this current? This is the induced current. The induced current, because you moved the bar magnet, is in this direction. And in the last chapter, you've seen that a current loop itself is a source of magnetic field. A current loop itself is a source of magnetic field. Or because of this current that is induced in this loop now starts having its own magnetic field. It has its own magnetic field. Now use your right hand rule. Use your right hand rule, and you will see that the magnetic field is going to be as given in this picture, with the north on this side and the south on this side. This is how the magnetic field, this you have seen in the previous chapter 33. Okay, the magnetic field for a circular loop of current is going to be like this, and this comes from the right hand rule. This comes from the right hand rule. So when you move the magnet closer and move the north pole of the magnet closer, you're basically going to have a magnetic field which is trying to enter into the loop. So what the loop does is it counteracts that increase in the magnetic flux by setting up its own current and its own magnetic field. Now look at the direction of that magnetic field, the direction of that induced magnetic field, because it is happening because of the induced current. We call this magnetic field as B induced. So this B induced is going to oppose the increase because of the bar magnet. The bar magnet increased the flux. So what happens is the flux, the induced current will set up its own magnetic field to oppose that increase. It is not opposing the direction of the magnetic field. It is not opposing the magnetic field. It is opposing the increase in the magnetic field. Which magnetic field? The magnetic field of the bar magnet. You're pushing the bar magnet like this. North pole is here. So you are increasing the flux. Okay, positive. You are increasing the flux. So what does this loop do? Loop will set up a current and sets up an induced magnetic field in the opposite direction to oppose this increase. Okay. Now, is this point clear, guys? Are you listening?
Yes, ma'am.
Okay, so the job of the loop, the induced EMF, the induced current, is to set up a magnetic field to oppose the increase in the applied flux. That's all. Okay. So now let us look at the second picture. In the second picture, okay, this is by somebody else. So this is another set of picture. So let's just discuss this picture once. So please try to understand this point. Okay, you're getting the North Pole, and this is your loop. Okay. So what is happening? The flux is increasing. The flux through the loop is increasing. d phi by dt is positive. So if d phi by dt is positive, your loop should set up a magnetic field to oppose that increase. So what happens is, see here, it is setting up a current as given by the purple arrow. It is setting up a current like this. That's an induced current. And because of that, from right hand rule, it is setting up a magnetic field in the opposite direction. It is setting up a magnetic field like this. Okay, or I will simply just draw a magnetic field and show that that magnetic field, the magnetic field induced, is going to oppose this increase. Because the increase was in this direction, it sets up a magnetic field in the opposite direction. Okay, and that can be shown instead of a bar magnet. Okay, or you can actually show the magnetic field setup like this. If this is the current induced in the loop, then look at the magnetic field. The magnetic field is such that your north is here. It is opposing the applied magnetic field and the increase in the flux. Please, again, I insist, it is not the direction of the applied force. It is the change in the flux that matters. It is not the direction of the applied field. Look at the second picture. You again have the same north pole looking towards your loop. But in this case, what is happening is you're pulling it out. When you're pulling it out, what will happen to the flux? Will it increase or decrease with time? The second picture. When you pull out the magnet, what will happen? What will happen to the flux? You can see that when these lines are all far away, no, these magnetic field lines are far away. So when you pull out,
Decrease.
decrease, there will be a decrease. So what happens is d phi b by dt will be negative. D phi b by dt will be negative. And what your circuit actually, that loop actually tries to do is, it does not like change. Basically, that loop does not like change. Whenever the flux is increasing, it sets up a magnetic field in the opposite direction. Here, in the second case, what is happening is the magnetic field applied is as in the same first situation only, okay? But here, the flux is decreasing. There is a decrease in the flux through it that it doesn't like. So what it does this time is, it sets up a current in the opposite direction. It sets up a current in the opposite direction so that it sets up a current like this, so that the flux is going to be in this direction. So that, okay, the magnetic field it is setting up is in this direction. Okay, so you look at the arrows here because of this induced current. So this is your induced current, and look at the magnetic field. So basically, you are able to conclude that the induced EMF and current are set up to oppose the change in flux. To oppose the change in flux. Okay, so it's not the direction of the magnetic field applied that matters. Okay, it is the change, it's a sign of the change that matters. If the change is positive, it sets up a field in the opposite direction. If the change is negative, it doesn't like that decrease. So it adds up by applying a field at. Okay, so what we have seen till now, this discussion is called your Lenz's law. This is what is Lenz's law. So Lenz's law put in a sentence is like this. The flux of the magnetic field due to the induced current. Read this carefully. It is a flux of the magnetic field due to the induced current. Okay, this will oppose the change in the flux. It will oppose the change in the flux. If the change in flux is positive, induced magnetic field is in the opposite direction. If the change in flux is negative, the induced magnetic flux is in the same direction. However, to draw these things, you have to know your right-hand rule. You have to know your right-hand rule. If you have a circular loop of current, put your hand in the direction of the current of the loop and look at the thumb. Thumb gives you the direction of the magnetic field. So if you know this, then you are comfortable with this. And this is called the Lenz's law. So applying Lenz's law to Faraday's law, you are now going to rewrite the equation. How are you going to write it? The induced EMF is proportional to modulus. Yesterday you wrote induced EMF is equal to d phi b by dt if there is only one turn, and if there are n turns, you put an n there and put a modulus. So this is your Faraday's law. But today we are going to incorporate Lenz's law into this and write induced EMF is equal to minus, this is crucial, minus d phi b by dt if there is one turn. If there are n turns, into n. Okay, and since yesterday I have been telling this, EMF is simply a voltage. EMF is an voltage difference that it is creating. So it is a voltage. So using Ohm's law, induced EMF is actually current induced into the resistance of that circular loop. It need not be circular. In all our examples to circular, it need not be circular. Okay, so what does Lenz's law do for you? Lenz's law gives you the direction of the induced EMF and the current. It gives you the direction of the induced EMF and the current. Madam, what is the meaning of direction of induced EMF? That I will explain. If you have a circuit and your EMF is this. Now tell me, will the current in this loop be clockwise or anti-clockwise? Will the current in this loop be clockwise or anti-clockwise? Clockwise. It will be clockwise. So this EMF direction is this. So what does this arrow mean? It is driving the current in this direction. So look at this. This is a positive higher potential, lower potential. So from a higher potential, the current flows through the wire to the lower potential. So this is the meaning of the sign of the induced EMF. Okay. And in turn, what is this induced EMF doing? Induced EMF is setting up its induced magnetic field. And what is that magnetic field doing? That magnetic field is opposing the change of the flux through it. Okay, here to see whether you are understanding the concept, I have just put an exercise for you. Let's see this. Okay, so here is a loop. This is a loop. Okay, there is no source of EMF. This is a loop. First you are applying, and the direction of the magnetic field is upward. Let it be uniform magnetic field. This is the initial magnetic field Bi. Okay. Then with time you are going to increase the magnetic field, so that I have shown with a larger arrow. So Bf finally. So what will be the direction of change? Direction of change will be in the upward direction only. Okay, that means there is an increase. So this is delta B. So if the change in the magnetic flux is in the same direction as the magnetic field applied, then according to Lenz's law, what should be the direction of the induced magnetic field? Flux is increasing. So what should be the direction of the induced magnetic field? Will it allow the increase or will it oppose the increase?
Oppose.
Oppose. So The increase is in this direction. So the opposition should be in this direction. So this should be the direction of the induced magnetic field. So now if you want to know what is the direction of the induced current, use your right hand rule. So this is the direction of the induced current. Now let's go to the second picture. In the second picture, again, the magnetic field through the loop is in the upward direction. Okay, but initial magnetic field is larger than the final magnetic field, which means the change in flux is negative. Change in flux is negative. Okay, therefore, what should your induced magnetic field do? It should oppose this decrease. So it should create a field and try to compensate that decrease. Therefore, the magnetic field will be in the upward direction. What you have applied will be in the induced magnetic field will be in the upward direction. And from the right hand rule, the current is as given here. Is this right, guys? So now what I have done here is I have the first two pictures. I've simply used magnetic field without using the word flux. Just using magnetic field, I have tried to explain. Now, in case you are not understanding, what is this delta B and having a direction? So delta B is actually BF minus BI. Okay, so vectorially, if BF is larger, then what is minus BI? Minus BI will be this. So BF minus BI will be a vector which is this. Are you understanding this? Vector addition. Okay, so that's how I have put these two, in case you're wondering what this means. Okay. The next two pictures, what I've done is I've tried to discuss in terms of flux. So these two pictures are going to be discussed in terms of the magnetic flux. Okay, magnetic flux is integral B dot dA. So that means area is also a vector. Area is also a vector. So now the question is, how do I fix an area? When it was Gauss law, okay, I had a closed surface, outward normal, you said. That is the direction of the area vector. But here, how do you fix the area vector? Area vector, because the loop is a plane, area vector can be either this or this. Either this or this. You decide what you want. Okay, so let us first fix our area vector as looking up. Let us fix our area vector as looking up like this. Okay. And now you're applying a magnetic field. Let it be a uniform magnetic field. The magnetic field is in the upward direction. So you're seeing that B and A are parallel to each other. B and A are parallel to each other. Therefore, flux is positive. Will you agree? Will you agree that flux is positive? Because B dot dA will be positive because B and A are parallel to each other. So flux is positive. In the next picture, you're seeing that the final magnetic field is increasing. If the final magnetic field is increasing, flux is still a positive number and its value has increased. Therefore, the change in flux is going to be d phi B by dt will be positive. How many of you understood what I've said? Do you want me to repeat this?
Yes.
Right. I'll once more repeat. I am talking in the second set of pictures in terms of flux because Lenz's law, Faraday's law, everything is in terms of flux. Okay. So flux is integral B dot dA, and if it is a uniform field, you can also write it B dot A. Okay. That means whether B dot A or integral B dot dA is positive or negative depends on the angle between B and A. If angle between B and A is, let us say, 0, if B and A are parallel to each other. So we will fix our A so that it is parallel to B. We will fix our A so that it is parallel to B. Initial magnetic field is a smaller arrow. The magnetic field is increasing, so it's a larger arrow after that. So you can see that the initial flux and the final flux are both positive. Are you understanding that now?
Yes, ma'am.
Right. And the final flux is more than the initial flux. That you're understanding?
Yes, ma'am.
Right. Therefore, d phi B by dt is positive. Is that fine?
Yes, ma'am.
Right. If d phi by dt is positive, according to Lenz's law, EMF should be negative. Right? Induced EMF is minus of d phi b by dt. This is what Lenz's law said. So if my d phi b by dt is positive, my EMF has to be negative. That means it has to set up an induced current and an induced magnetic field to oppose this flux. So listen very carefully what we are going to, what I'm going to just say now. You listen very, very carefully. I kept my area vector like this. If my area vector is like this, my positive current is like this, given by a right-hand rule. My positive current is this. Okay, if there is an induced positive current, the positive current will be like this, and this is my area vector. But what did I just now get? D phi by dt is positive, therefore EMF is negative. If EMF is negative, induced current is negative. Induced current is negative. If induced current was positive, it would have been like this. But since induced current is negative, it is going to be like this. See this picture. Because it is negative, it is the opposite of what should have been positive. Are you following this? Maybe I'll go for another example, then you will understand better. In the second example, go to the picture below. Again, we are talking of area vector. We want to keep it parallel to the B vector. Okay, so it is upward. We can fix it the way we want, okay? So we are fixing it parallel to B. Always try to fix it parallel to B. Then you're seeing that the magnetic field initially is larger. Finally, it is smaller. Flux is positive in both the cases. Initial and final, the flux is positive because B and A are parallel. But flux is decreasing because the magnetic field went down, flux is decreasing. Flux is decreasing means d phi by dt is negative. If d phi by dt is negative, then according to Lenz's law, EMF has to be, if d phi by dt is negative, EMF has to be positive. That's what Lenz's law said. It will be positive. Okay. So EMF has to be positive. EMF has to be positive means go with your area vector, curl your finger like this. Whatever is the direction of the finger, that is the direction of the induced current. Okay. So always take your area vector, curl your fingers. That finger direction gives you the direction of positive current. If your answer is coming positive, mark that arrow. That is the direction of the current. If your EMF is coming out to be negative, then put a direction opposite. So this is the way you have to decide the direction. Okay, here for example, you can just go through this. Here what I have done is I have taken the area vector. I told you area vector you can take the way you want. Area vector we have taken in the downward direction, anti-parallel to B. Anti-parallel to B. So what happens is the flux is a negative quantity. Then because the magnetic field is increasing, the flux becomes more negative. Okay, therefore change in flux is negative. So don't bother about it. 3 and 4 are unnecessary mathematical complications that you will be inflicting on yourself. Okay, like for example, initial flux is -4, final flux is -8. Then what is the direction of change in flux? Why do you want to kill yourself? Don't do that. Okay, so I have just tried to put these pictures to tell you, don't venture into unnecessary adventures. Nothing wrong. Nothing wrong with what I have done there. But why do you want to make your life complex by doing this? Always be smart, deal with positive numbers. So dealing with positive numbers means keep your area vector parallel to B. Okay, so now okay, so whatever I said is what is given here. If the area vector is upward, curl your right hand. Okay, that gives the direction of the induced EMF and the direction of the current. So that's what he's trying to tell you. Okay, and this picture says something more. Come to the first picture here, that says something more. Let us say I have a circuit. Let's say I have a circuit with 4 volts connected to 2 volts connected to my induced EMF. Okay, and let the induced EMF be 8 volts. Okay, now what you have to now do here is look at which of this is finally dominating. Which is the effect that is going to dominate? Okay, 4 volts would have driven the current like this. 2 volts would have driven the current like this. This would drive the current like this. So what will be the net EMF? Anyone? What will be the net EMF? Anyone? Can you see this entire thing in a series? So 8 and 2 will add up and give you 10 volts. Okay, you can show it like this. 4 volts. This will become 10 volts. Okay, let's say there is another resistor here. Okay, can you see the polarities are such that, wait, 1 sec. What did I say? Current goes from to positive. Well, I made a mistake here, 1 sec. Right. The current will drive like this. The current will drive like, the current will be driven like this. So 8 and 4 will add up. So you are going to have 8 and 4 will add up. Let me just draw it again. 8 and 4 will add up and you're going to have 12 volts, 2 volts. Can you guess what will be the direction of the flow of current? Is it going to be clockwise or anti-clockwise? Clockwise or anti-clockwise? This is the direction of the current. So basically, it is just this. We kept on telling in the last class that you are having a loop without EMF, you are having a loop without EMF source. That was basically to get home that idea that even if there is no EMF source, you are going to have a current. Okay. Now, can Lenz's law and Faraday's law be applied to a circuit with an EMF source? It can be applied. It can be applied. Only thing is you have to see whether your EMF that you induce is going to be greater than the EMF of the circuit. If it is greater than the EMF of the circuit, then this direction will dominate. If on the other hand, your EMF in the circuit, which is already there, is going to be greater than the EMF induced. Okay, and then what happens is the effect of the circuit EMF will be more. But then you can talk about an effective EMF. So that's what this figure is trying to show you. Yeah, so let's try this problem, guys. Let's try this. You have a circular loop. You have a circular loop of wire of radius 0.32 meters. Radius r equal to 0.32 meters. The resistance of the wire is 2.5 ohm and it is placed in a uniform magnetic field. Look at the direction of the magnetic field. The magnetic field is like this into the plane of the screen. Okay. And it is a uniform magnetic field and perpendicular to the plane of the sheet. And the magnetic field is varying as a function of time. It is given in Tesla. It is varying as a function of time. Now you have to find out the magnitude and direction of the current in the loop. You have to find out what is the direction of the current in the loop. So what I will do here is I will simply just forget this. Let's quickly do the problem. So what we can do is let us assume that okay. So what we'll do here is we will Okay, let's make an assumption that I kept telling you about the area vector, remember? So in this problem, we are going to use that concept. So here what we are going to do is, magnetic field is into the plane of the screen. It is into the plane of the screen. So let us keep our area also into the plane of the screen. So if the area is into the plane of the screen, then your positive, immediately, as soon as you fix your area, then immediately look at the direction of the induced current, positive induced current. It should be like this, sorry. Positive induced current will be, positive induced current is going to be in this direction. If it is positive, if EMF is positive, I induced is positive, I should get it like this. Okay. How did I do that? I did that by using the right hand rule. Area is like this, so turn the fingers and then do it. Okay, next. B is given. So what is my flux? Flux is going to be BA. Flux is going to be B into A. It is simply B into A because my magnetic field is uniform and it is parallel to the A vector. It's B into A. So now let us look at what is d phi B by dt. d phi B by dt is going to be dB by dt into A. This is simple calculus. Okay. A is the area is a constant. So area you cannot differentiate. So you differentiate your B. So it's going to be dB by dt into A. Yes. Okay. dB by dt into A. And I want to know what is the magnitude of the current and the direction of the current in the loop at t equal to 1 second. At t equal to 1 second. So what I'll do is, first I will get my dB by dt. What is dB by dt? Take this equation and differentiate. Minus 4 Tesla is a constant. Minus 5.6 T will be there. So minus 5.6 it will become. And then here it is 2.2 T square. So it will become plus 4.4 T. T is 1 second. So put T equal to 1. Okay. Therefore, if I do this, I'm going to get minus 1.2 will be dB by dt. That will be dB by dt. So now let me put this here. dB by dt is minus 1.2. And what is my area? Area is going to be pi r square. Okay, so minus 1.2 into pi into, what is the radius? Radius is given as 0.32. So into 0.32 square. Okay, so if I do this, I get my d phi b by dt. I get it as, if I by dt, I get it as 0.39 volts. I will get it as minus 0.39 volts. I'm getting this as my d phi b by dt. But I know that my EMF is equal to current into the radius of the loop equal to minus d phi b by dt. Okay. Therefore, I can say that my EMF induced is going to be equal to plus 0.39 volt. Because d phi by dt is negative, okay, I'm getting my phi induced as positive. Okay. And now let us use Ohm's law here. Therefore, I can say that current induced is also going to be positive. It is going to be EMF induced divided by R. EMF induced is 0.39 divided by R is resistance is 2.5 ohm. 2.5. Okay, so you will get your answer in ampere. Now, if my induced current is positive, this is what I should have got. Yes, my induced EMF and current are positive. So I will get my direction as this. The book is doing this problem slightly differently. Okay, he's taking z-axis, then minus z-axis, he's taking area along the minus z-axis. It is more complicated. Don't bother to do all that. You will get the same answer without going through all that thing. This is much more simpler. What I have just done is much more simpler. So go with this. Did you understand this problem, guys? What is the induced EMF because of the changing magnetic field at a time t equal to 1 second? So what I have done here is, first thing is I have done dB by dt. And dB by dt I have found at a time t equal to 1 second. I'm getting this. Then I kept my area vector as into the plane of the screen so that it is parallel to my B vector. So B dot dA is positive, flux is positive. And now I'm getting flux as A into dB by dt. Okay, because I'll write one more step here. d phi by dt is actually equal to d by dt of dA. So which will be dB by dt into A. Okay, so dB by dt I got it as minus 1.2. Then area is pi r square. So just put it, you will get EMF, d phi by dt negative. D phi by dt is negative, therefore EMF is positive, therefore current is positive. Positive means as given there. Yeah, so what he has done is, he has put some extra minus signs. You're going to see two extra minus signs, nothing else. What he has done is, he's taking that direction into the plane of the screen as minus z. So B is also negative, A is also negative, negative into negative, positive, that's all, nothing else. But you need not do all that. Without that also, you're going to get your answer. Okay? Direction. Okay, so this is at a time t equal to 1. The book is also talking about another time. Okay. Okay, now the next thing is, how do you change flux? So by now you understood that flux change is important, not magnetic field change. Flux change. If a flux changes through a loop, there will be an induced EMF and an induced current. Okay, so what are the ways by which you can change the flux? One thing is, move a magnet relative to the loop. That's what we have done. The bar magnet was moved. So by moving the bar magnet, you are changing the magnetic field through the area, thereby changing the flux. That is one way. Second is changing a current in a nearby circuit. Changing a current in a nearby circuit. That was Faraday's experiment 2. Your original loop was there. He had a loop 2. In that loop 2, he kept changing the current by opening and closing the key. Okay. The same principle happens in the case of a transformer also. Here, in the case of a transformer also, it's the same thing that happens. Okay, so this is one loop. So this is one loop. This is the primary loop. So in the primary loop, he is going to simply apply a voltage and keep changing the current. Okay, by changing this current, there is a change in magnetic flux, which is because after all, a current loop is a magnetic field source. So when the current is changing, the magnetic field is changing. When the magnetic field is changing, the flux through the second loop is changing. Therefore, there is going to be an induced current. You look at this loop on the right. Look at the loop on the right. The loop on the right is having a bulb, but then it is not having any EMF source. That EMF came because the flux through this is changing. The flux changed because you have applied an AC current to the original, that coil. That first coil on the left is called the primary. The one on the right is called the secondary. Secondary is not having any source of current, no source of EMF. It is getting an EMF which is induced because of the change in the flux that was created by the primary. And this flux is getting transmitted through this magnetic material. You're seeing one rectangular shaped piece, no? That's actually a magnetic material. That's the core of the magnet. This is how a transformer works. So changing current in one loop induces a current in the second loop. So this is how a transformer works. Now what's the third method? The third method, moving a loop in a non-uniform field or changing the area of the loop lying in the field. Changing the area of the loop lying in the field. I'll give you another picture for that. Look at this. Here, there is a loop. This is a defined area of uniform magnetic field, and you're dropping a coil. When you're dropping a coil, this coil doesn't have any flux because it's completely out of the magnetic field. So no current will be there. Flux is zero, it's a constant. But look at this. When it is entering, what is happening? When it's entering, what is happening? You're seeing the blue shaded area, which is increasing as it keeps entering. That means flux is increasing. That means flux is increasing. And what is the direction of the flux? The flux is this. Area vector is this. Okay. Therefore, positive current would have been this. But then because it is increasing, EMF will be negative. So there will be an induced current. Then after it fully enters, what is happening? The flux is a constant. It is non-zero, but it's a constant. So all the way here, there will be no current. Now, when it is emerging out of the magnetic field area, what is happening? The area, this blue shaded area, is decreasing as a function of time. So what happens? Flux is decreasing. Because flux is decreasing, a current will be set up in the opposite direction. And finally, when it is completely outside, no current because flux is zero and it is not changing with time. So here in this example, you are actually moving a coil through a region of magnetic field. Okay, I'm changing the flux. Okay, similarly, look at this picture. This is also an example of the same. You have a current carrying wire. Look at the picture on the right. You have a current carrying wire carrying a current I. So according to your Ohm's law, according to your magnetic field laws, what should be the direction of the magnetic field? The direction of the magnetic field is going to be like this. This will be the direction of the magnetic field. Okay, and please remember, the magnetic field will be larger near the wire and sparser as you move away. And sparser as you move away. So by allowing this coil to fall like this, fall vertically down, you are bringing it from a region where the flux is going to be smaller to a region where the flux is going to be larger. So you're actually changing the flux by allowing it to fall through a non-uniform magnetic region. So because of that, there is a current induced. You can just use your Lenz's law and see what is happening. The field is increasing, flux is increasing, area vector is this. Therefore, positive should have been this, but then because it is in, d phi by dt is positive, EMF will be negative, so therefore the current will be like this. Okay, so this is one way of creating induced current and EMF. Then next, let us look at the fourth method. The fourth method is rotating a loop in a fixed magnetic field. By rotating a loop in a fixed magnetic field. For that, I'll give you an example. The example here will be a generator. In a generator, what happens is you have a loop. This loop is not having any source of EMF, but there is a magnetic field as given by this purple arrow. Okay, so now you turn this loop. This was the start of our chapter. Our chapter itself, we started like this only. What if you'd give a torque if you turn a loop? That's what is happening here. You turn the loop. When you turn the loop, what is going to happen is there will be a change in theta by rotating the loop. There is a change in theta. What is theta? Theta is the angle between the B vector and the A vector. A vector, and let's say this is my B vector, this is theta. So by rotating that loop, you're actually changing the angle. When you're changing the angle, flux will be B dot A. B dot A will be BA cos theta. Please remember, guys, look at this. This is your phi B. Now, what will be d phi B by dt? Here you see B and A will be constants. They will remain like this. and you will have d by dt of cos theta. D by dt of cos theta. Theta becomes your variable. So like this, the flux will change. And because the flux is changing, there will be an induced current in the loop. This is the principle behind a generator. Then the last one is changing the size or shape of the loop. What is flux? Flux is integral B dot dA for a closed loop. What if the loop is going to change area with time? If it's going to increase with time, then flux will increase. If it's going to decrease with time, flux will decrease. So like that also you can produce induced EMF or induced current. These are typical questions that one could ask in MCQs. Guys, is it all clear? These examples are all not dealt with in the book. I am only putting all this. Are you understanding?
Yes, ma'am.
Yeah.
Yes, ma'am.
Okay. So in the next class, what we'll do is we'll start with motional EMF. So that's also similar to what we have done here. What that ring was falling through a region, no? So something similar is what is called motional EMF. You're going to pull a loop in and out of a magnetic field and see what happens. Okay, and that has got some very interesting applications also. We'll see that in the next class. God, I should finish so much in the next class. When I get involved, I start talking a lot. I shouldn't have done that. Okay, so I think I'll stop here. So you guys can leave.
Thank you.